In this section 2.2 limits, at the end of the section, the student should be able to determine if a limit of a function exists as x approaches a real number a. This section is kind of the end or the summary of the last section about one-sided limits. One-sided limits, we were talking about the left side, the right side, kind of one end at a time. This time gonna be both ends. So kind of in the big picture, as x approaches the value a, what's going on with the function f of x, or f of x approaches to what value. So the limit defined informally if a value of the function f of x get closer to some value L, as values of x that are smaller than some number a and values of x that are greater than the value a get closer and closer to a. So basically, if x getting closer to a negative, that means x is smaller. X approaching a positive, that means x is slightly greater than a. That's what we looked at last time in the section 2.1 or one-sided limit, left hand limit, right hand limit. So we're looking at both directions at the same time. If both directions give us the trend of the function f of x approaches to the value L, we say that L is the limit of the function f of x as x approaches a. And then for the notation, similar to the last section, the limit LAM as x approaches a, this time no superscripts. That means it's understood to be like coming from both sides, the left side, the right side of the function of f of x approaching to the value L. So when you read it the limit of f of x as x approaches a equal L. Next, we're gonna look at what cases the limit will be existent. The limit of the function f as x approaches a real number a exists if and only if the limit x approaches a of the function f of x equals L, where L is a real number. The second case, if the left-hand limit not equal to the right-hand limit, then the two-sided limit does not exist. So when it comes to does not exist, we use the short term like D and E. So the other way we say like if the value coming from the left not equal to the value coming from the right, if they are not the same, so we can say that the limit of the function f of x as x approaches a does not exist, or the two-sided limit doesn't exist. And case number 3, if the limit of the function f of x as x approaches a equals positive infinity, that means the function grows or increases without bound as x approaches a from the left and from the right, or the function is decreasing without bound from the left and from the right, that means it comes toward to the negative or positive infinity, which is just a symbol of very, very large quantity. So we can also say the two-sided limit does not exist. But in this case, most likely we just mention about either positive infinity or negative infinity. Next case, the indeterminate forms and algebraic solutions. In any limit problem, if the numerator has a limit different from 0, and if the denominator is 0, then the limit of the quotient must fail to exist. So in the case that, for example, we have the limit of x minus 1 over x as x approaches 0. If you plug the value into the x for the numerator, we got negative 1, 0, and the denominator got 0. So this is a case that is talking about does not exist. The next case, however, if both the separate limits of the numerator and denominator are 0, then there may be a limit for the quotient, maybe, so we have to use the other strategy to find the limit. So this way, the family factorization or factoring skill that you guys look at in the previous math courses, like in, for example, in college algebra, you're gonna use that skill or factoring skill to simplify the expression and then attempt to do the limit again. For example, if we have the limit of the x squared minus 1 over x minus 1, similar to the example that we saw in the last section, sorry, x approaches 1, not 0. So in this case, if you replace the value x with the 1, we're going to get 0 on the top, 0 on the bottom. So this one is called indeterminate form. Which we are not sure yet whether the limit does exist or not. So in this case, we're going to factor completely. So like, for example, x minus 1, x plus 1 for the numerator part, and divided by denominator x minus 1. And then we can see the factors top and bottom reduce. Therefore, the expression is simplified to be just x plus 1. And we find the limit as x approaches 1. When it comes down to this case, we have the expression as the polynomial. Recall the limit of polynomial is the same as the polynomial as the value of that polynomial function. So we just plug it in wherever x is. So plug it in 1, so 1 plus 1 equals 2. So that's just a quick example of the indeterminate form case. Next, we're gonna look at the example. The first part here, we just use the graph to determine the left side, the right side, and then the two-sided limit. As you see, A, B, and C, the A is 0, 0, 0, but A is the left-hand limit, B is the right-hand limit. So that means the part A, x is slightly less than 0, part B, x slightly greater than 0, but part C, we are going to look at these two values, whether they are the same or not. Let's get started wherever 0 is, so right here. So we're gonna look at the left hand limit. So as we move along the graph toward 2, x equals 0, the y approaching to the value 3. So we put the answer here for part A, and then use different color for the right hand limit. So for the right hand limit, as x approaches 0, moving along the curve from the right side of the 0. Again, the graph tells us that the behavior of the function approaching to the same value 3. So the left hand, the right hand, they are coming toward to the same number. Therefore, the two-sided limit in part C has the same value. Let's move on to D, E, and F. This time, the A is 2, so the 2 is right there. And the first part, part D, x approaches 2 positive. That means we look at the right-hand limit, or x is slightly greater than 2. If x is slightly greater than 2, we look at the right part of the graph, moving along the curve here, the trend of the graph approaching to the value 2. So equals 2. So we can make a note here, right here, as x approaches to positive, y approaches to the value 2. And now we're gonna look at the left-hand limit. I use different color. The left-hand limit at the point 2 here as the x, so we look at the left part of the graph because this is the left-hand limit. X is slightly less than 2. As you move along the curve toward to the value 2 from the left side, the value of the function approaching to the value -1. Or to wrap up here, at that point on this end, as x approaches 2 from the left, y approaches -1. So that's the left-hand limit value, and this is the right-hand limit value. Now D and E, they are not coming to the same value. Therefore, the limit as x approaches 2, as you see, like no superscript, so that means we're gonna make a conclusion whether the both ends coming toward to the same number or not. In D and E, they are not coming to the same number, so therefore, the limit as x approaches 2 of the function f of x does not exist. So D and E. I'm going to put a note here because the limit of the function as x approaches to from the left not equal to the limit of the function f of x as x approaches to from the right, where a, b, and c, the limit exists because, put the reason here, because the limit of the function f of x as x approaches 0 negative equals the limit of the function f of x as x approaches 0 positive. So going to be two cases to see whether the limit of the function as x approaches a exists or doesn't exist by looking at both directions coming to the same number or not. Next, we're gonna look at more examples involving algebraic expression and using the factoring skill in finding the limit value.